We've seen that using an insulator, in this case air, to carry current is impractical because very high and dangerous voltage is required. On the other hand, when a good conductor is used, too much current flows and destroys the conductor. We require a happy medium, a material that will allow enough current to flow to do the job without burning up the conductor, and at the same time, of course, using a low, safe voltage. Let's look at this again. Connecting this wire across the battery, it doesn't burn up. It starts to heat up until it's red hot, but it doesn't allow too much current to flow. The reason that it doesn't burn up is because this is a semiconductor material. It offers resistance to current flow, opposition to the movement of electrons. By introducing resistance into the circuit, then current can be controlled. In this lesson, we'll discuss the factors that determine resistance, and we'll talk about resistors, devices that are designed to offer specific amounts of resistance. Now, we've seen the effects of resistance many times in previous lessons. For example, why didn't this light bulb burn up when we connected it across the battery? Well, it limits the current to the amount required to produce light. If it didn't limit current, it would burn up. So the bulb offers resistance to current flow. It's obvious then that we need resistance to control current. But why do some materials offer a lot of opposition and others very little? Basically, it's the atomic structure of the material. For example, we've said that conductors have many free electrons. They allow current to flow with ease. If conductors don't oppose current, then they must have very little resistance. Well, that's why the wire burned up earlier. It was a copper conductor. On the other hand, insulators have very few free electrons. In most cases, they prevent current flow. Insulators then have a high resistance. That's why a large voltage was required to move electrons through air. A low resistance here, a high resistance here. But what about these materials? Their characteristics are between conductors and insulators. Then, using semiconductor materials, we can control current from a very small value to a very large value. Now, there are several factors that determine the resistance of semiconductor materials, but the primary one is the number of free electrons they contain. In other words, the material they're made of. So remember, the materials used to make up the semiconductor is the prime factor. There are some more. Let's look at them. These are length and diameter. Now, to show this, we'll use this bulb, these batteries, and 3 wires made of semiconductor material, nickel and chromium to be specific. Let's look at the wires. This one is very small in diameter. The next one is a little larger, while the third one is very large in diameter. Now, the wires are the same length. Before we begin, let's check the intensity of the bulb with just the resistance of the bulb opposing the current from the battery. As you can see, the bulb is lit very much, very bright. Now, in the first example, we'll use the small wire, and we'll see the factor length and how it affects resistance. Now, with the connection here and here, the battery must force current through the resistance of the bulb plus the resistance of this wire. There's very little current through the bulb. It's hardly glowing. Now, what I'm going to do, I'll slide this connection down the length of this semiconductor material. In other words, I'll decrease the length, and we'll see how it affects resistance. Okay, let's watch it. Very little current there. Decreasing the length, notice that the bulb starts to glow more and more. Now, let's stop right here. I've decreased length. I've increased the current. So the resistance must have decreased. There's more current through the bulb. Well, let's go on down to the end of the wire. Watch the bulb. As I decrease length, I decrease resistance because the bulb is glowing more. Well, this is pretty obvious. Let's take a look at it. When I had the bulb over here, the electrons had to travel the full length of this resistance material. So it's only natural that it's going to encounter more opposition. But as I decreased the length, I decreased resistance, and the bulb glows brighter. Then length is definitely a factor that determines resistance. Now in the next one, we're going to increase the diameter of the wire. Let's see what happens to resistance as we do this. Of course, with a small diameter wire, there's very little current through the bulb. Let's go to the next one. As I increase diameter, there's more current through the bulb. This means that resistance decreased. Let's go to the next one. Increased diameter, more current through the bulb. So resistance must have decreased. Now, let's make sure that we understand this. Let's do it again. With a small diameter wire, very little current, a large resistance. Increasing diameter, we decreased resistance. Increasing diameter again, decreased resistance. This is also easily understood. This in view of a large and small wire shows that the large wire contains more atoms. With more atoms, there are more electrons available. And with more electrons available, it will pass current easier than the small wire. Then as the diameter of the material increases, its resistance decreases. Now, the third factor that determines resistance is the temperature coefficient of the material. Temperature coefficient simply means the effect that temperature has on the resistance. To show the effect of temperature, we'll use a piece of tungsten. This filament from an ordinary light bulb is made of tungsten and will do the job very well. First, let me check the bulb to make sure that everything is all right. Okay, that's just the resistance of the bulb opposing current. Now I'll add the tungsten to the circuit. And you can see that it had a little bit of effect on current because it did decrease the intensity. But when it's cool, it has a small effect on resistance. Now to apply heat to the material, I'll use a small torch, so let me light it and set the flame so that it's just about right. Now, watch the intensity of the bulb as I heat the tungsten. Applying heat to it, notice that the bulb goes out. The resistance of the tungsten has gone up, which reduced the current through the bulb. Now, when I take the heat away and the tungsten starts to cool off, its resistance goes down because there's now current through the bulb. Now, let's try it again to make sure you understand what I'm doing. As I apply heat to the tungsten, its resistance goes up, there's less current through the bulb. When I remove the heat, the tungsten cools, resistance goes down, current through the bulb increases. Now, if resistance goes up when the material gets hotter, as it did in this case, the material has a positive temperature coefficient. Tungsten then has a positive temperature coefficient. In the next example, let's use a piece of germanium. Now, I'm going to decrease the flame just a little bit. Let's try a piece of germanium, heat it, and see what happens. First, let me check out the circuit. Okay, there's the bulb without the germanium. Okay, now I'll add germanium to the circuit. Remember, the germanium is now opposing current. As you can see, the bulb is out, indicating that the resistance of the germanium is so large that it prevents current through the bulb. Now, watch what happens when I apply heat to the germanium. Its resistance must have gone down because the current through the bulb increased. Now, watch the bulb, though, as the germanium starts to cool off. As it cools, its resistance goes back up, stopping the current through the bulb again. Okay, let's try this one more time. Applying heat to the germanium, its resistance goes down, current through the bulb. But as the germanium cools off, its resistance increases and will stop current through the bulb. Now, materials that exhibit this property have a negative temperature coefficient. And I might add here that most materials will exhibit a positive temperature coefficient. Okay, length, diameter, and temperature coefficient are all factors that determine the resistance. Now, remember also, the materials, the combination of materials used to make up these resistive devices will determine resistance. Now, since different circuits will require various amounts of resistance, there's a requirement for measuring the amount of resistance. Well, resistance is measured in units called ohms, O-H-M, ohm. Now, here's what an ohm is. If there's 1 ohm in the circuit, let's say this is 1 ohm, 1 volt will cause 1 ampere of current. So remember, 1 ohm of resistance means that it will limit the current from a 1 volt source to 1 ampere. Now, the symbol for resistance is the capital letter R. And remember, it's measured in ohms. Now, to provide the various resistances needed in electronics, devices with specific ohmic values have been developed. These devices are called resistors, and basically they're semiconductor materials. Now, by semiconductor material, I mean that they are not a good conductor. They're not a good insulator. They exhibit characteristics between these two. Let's look then at some common resistor types.